Hello everyone, my name is Karan Mashru. Welcome to this video. And in this video, we are going to look at the solutions of the problems asked in GFG Weekly Coding Contest. So first of all, let us start with the first question, that is winner team. Now, first of all, I'll explain you this question on OneNote along with the help of an example, and then we'll go through this question description line by line so that you'll understand it better. Okay, and then we'll think about the solution. So basically, in this first question, that is winner team, we are given three teams X, Y, and Z. Okay, and each of these teams contains n players each. Okay. Now, each of these n players, their powers are given to us. Okay, so we have an array X in which there are n elements, which denotes the power of the n players of the team X. We have an array Y in which there are n elements, which denotes the power of n players of team Y, and we have a team Z which in which there are n elements, which denotes the power of the players of the n players of team Z. Okay, so now what will happen, starting from the leftmost player, one player from each team will compete, and the player with the highest power will stay and the other two will be disqualified. Then the next player from that team will participate. So for example, let's say we have an array X 3, 5, 1, 7, 9, array Y as 2, 8, 1, 3, 6, and array Z as 1, 7, 8, 1, and 9, let's say. So first of all, this is X, this is Y, and this is Z. Okay. So first of all, these three players will compete, and the one with the highest power will stay, other two will be disqualified. So these two will be disqualified. Now the next players from this teams will compete. So, but this three only will remain. Why? Because it has not lost. So 3, 8, and 7, this will compete. So 7 and 3 will be disqualified. Now 5, 8, and 8 will compete. Now whenever the powers are same, at that time the team with the lower, like the first alphabetical character or the lower lexicographical rank will win. So whenever the power is same, so if the power is same between X and Y, X will win. If the power is same between Y and Z, Y will win. If the power is same between X and Z, X will win. And if the power is same in X, Y, and Z, all three, then X will win. Okay. So here we have 5, 8, and 8. So 5 will disqualify. Now 8 and 8 is same. So here Y will win and Z will disqualify. Okay, Y will get more priority. Now 1, 8, and 1 will compete. So 1, 8, and 1. So again 1 and 1 will disqualify and 8 will remain. Now 7, 8, and 9 will compete. So 8 and 7 will disqualify. Now 9, 1, and 9 will compete. So 1 will obviously disqualify. Player with power 9 and 9. Your X will get more priority, so this will be disqualified. Okay. Now we have this process will continue till only one team is left. So now 3 and 6 will participate. So 3 will be disqualified. And 6 and 9, 6 will disqualify. So the last player remaining is 9. So the winning team is X. So if team X wins, we need to print 0. If team Y wins, we need to print 1. And if team Z wins, we need to print 2. That's basically the question. Okay. Now let's go through the question line by line. You are watching an exciting match between three teams X, Y, and Z. Each team consists of n players and each player has a specific power value. Okay. The match will proceed as follows. In each round, the first available player, the next player who hasn't been disqualified, means let's say there are n players. First two is disqualified, so the third player. The first available player who has not disqualified from the left, मतलब कि हम लेफ्ट टू राइट जा रहे हैं, 0 इंडेक्स to n-1 index. From each team will compete. From every team, one player will compete. The player with the greatest power in each round wins the match and proceeds to the next round. So the one which has the greatest power will stay. The two losing players will be disqualified and eliminated from the further rounds. They will not participate in further rounds. After each round, the winner will compete against the next available players from the two teams that lost the previous round. So let's say a player from team Y wins, then team players from team X and Z will be eliminated, and the next players available in team X and Z will be taken and compete with the player Y, from team Y. If multiple players have the same power value in a round, priority is given to the player from the team with the lowest alphabetical order. So team X is prioritized over Y and Y over Z. Okay. a team loses if all of its players have been disqualified. So if all the players are gone, then that team loses. The game continues until only one team has players left out. So until there is only one team which has players left, the game continues. Your task is to determine which will win the match, which team will win the match, that we need to tell. Return a single integer 0 if team X wins, 1 if Y wins, and 2 if Z wins. Okay. So now if we think about the solution, so ultimately if you think the team which has the player with the highest power overall will win. The team which has the player with the highest power overall, okay, among all the 3n players, the team which has the player with the highest power will win. Because let's say we have some players in X, we have some players in Y, and some players in Z. There is a player in team Y which has the highest power among all the 3n team members. So ultimately, when this player will come into picture from team Y, the players from team X and Z will keep disqualifying one after the other. For example, let's say your player Y had a player with power 10, which is the highest in all the 3n players. So one after the other, players from X and Y will X and Z will keep disqualifying with respect to this player. So ultimately, this player, because of this player, team Y will win. So the team which has the player which has the highest power among all the 3n team members, that team will win. And if multiple teams have players with the same highest power, then in that case X will be given priority, then Y, and then Z. Right? So now we need to find which team has the highest power player. Okay. So what I can do is, first of all, I'll find the highest power player. I'll find the highest power player from team X, and I'll say that my answer is 0. So team X is going to win. This is what I'll say. Now I'll traverse through team Y and see if there is any player whose power is more than the highest power determined till now from team X. So if there is a player in team Y whose power is more than the highest power from team X, I will update my answer to answer 1. And if again I will traverse team Z, and if I find any player in team Z whose power is more than the highest power determined till now from team X and team Y, then I will update my answer to 2. Okay, so that will be the solution. So now let's look at the code. So I'll directly take the solution. So I have said answer equal to 0. So by default, I'm assuming X is the answer. X is the winning team, N as the size of the array, and P will be the maximum power determined till now. So I will say P is equal to X of 0, and then I'll traverse from 1 to N minus 1. And if X of I, that is the power of the ith player in the X team, is more than highest power determined till now, then power equal to X of I. So by the end of this loop, I will have the highest power from team X, and answer will be 0. Now I'll traverse the array Y, and if I get the power of any player in team Y greater than P, then I'll update P and I'll make answer equal to 1. Now I'll traverse through the Z array, and if I find any player's power greater than the highest power found till now, then I update P and make answer equal to 2 and then return the answer. Okay. So this will be the solution. The time complexity will be big of N. I hope you have understood this solution. Let's move on to the next question. So now let's understand the second question, that is operations on numbers. You are given two positive integers A and B. So we are given two positive integers A and B. Your goal is to make the values of A and B equal by performing a series of operations on B. We want A and B to be equal finally, and we can perform operations only on B. You are allowed to perform only two types of operations on B. So there are two valid operations which you can perform on B. First, if B is a perfect square, you can set B equal to the square root of B. So for example, if B is 36, you can directly convert it to 6. Second, decrease the value of B by 1. So let's say if it is 27, you can make it 26. Also remember, it's not necessary then that when it's a perfect square, you need to convert it to square root of B. So for example, if it is 36, but you want to convert it to 35, that is also allowed. But these are two available operations with the help of which you need to make A and B equal. Your task is to find the minimum number of operations required to make B equal to A. So what will be the minimum number of operations required where each operation will be either of these two operations such that you make A and B equal. If it is not possible, then you return, if it is not possible to make B equal to A, then return -1. If it is not possible, again, return -1. So let's think about this solution. So you are given two positive integers A and B which you want to make equal in minimum number of operations. In one operations, now you can do, there are two available operations, both the operations you can perform on B only. So you can either decrease the value of B by 1, or you can say B is equal to square root of B only if B is a perfect square. So B can be, let's say, 36 or 49 or 100 or something like that, okay? So you can do this only if B is perfect square. Okay, then only you can convert it to its square root. So what will be the minimum operations to convert B to make A equal to B? Now one thing which we can directly observe is either we do B equal to B minus 1 or we do B equal to square root of B. We are going to decrease the value of B. So this making A and B equal, this is only possible if B is greater than or equal to A, otherwise not. Okay, so if A is greater than B already, since we cannot increase the value of B, we cannot make A equal to B. So if A is greater than B, then you directly return -1. Okay, now, suppose A is less than or equal to B. Now that's the second case remaining. So you can perform either this operation or this operation. Okay. Now, what you want is, you want to convert A equal to B in minimum number of operations. So, what do we mean by minimum number of operations? So, what should we think with the help of which we will get minimum number of operations? Let's say this is my y-axis and the value of A is somewhere here. This is 0 and the value of B is somewhere here. So, I want to decrease the value of B to A to make them equal. So, if I want minimum operations to convert B to A, it means that in one operation, I need to decrease the value of B as long as possible. In one operation, decrease B as large as possible. Okay? So, for example, if I keep doing, let's say a very simple example, if B is, let's say, 101 and A is 10. So one way is to do B minus minus 91 times. Just keep doing B minus minus. Another way is do B minus minus 1 time. So B will get converted to 100 and then make B equal to square root of B. So B will be equal to 10. So this is one operation and this is two operation. In two operation only you got B equal to A. Right? Why? Because in one operation we decrease the value of B as large as possible so that we can reach nearer to A. For example, if this is B and this is A, so in one operation you made B this much less, in second operation this much, and in third operation this much. So in three operations you made A equal to B. Other way could be to keep doing B minus minus, okay, and just let's say it will take you, I don't know, let's say 120 steps, okay. So in one step you need to decrease B as much as possible, okay. So now see, there are some things to notice. First of all, you can, so what you want is, you want to convert B to square root of B, right? But you can convert B to square root of B only if B is a perfect square. So let's take two cases, that B is a perfect square, like 100, 36 and all, and it is not. So if it is not, then there is no doubt. You just need to do B minus minus, okay? But while implementation, you will do it more optimally. That I will come there, okay? If it's a perfect square, you need to convert B equal to square root of B. But there is one condition in this, okay? So if B is a perfect square, you convert B equal to square root of B only if square root of B is greater than equal to A. Because you cannot increase the value of B. For example, B is 36 and A is 10. Now, if you convert B to square root of B, it will become 6. Now, you cannot increase the value of B. So, you cannot make A and B equal at any time. So, you have to do B minus minus 16 times to make A and B equal. So, even if B was a perfect square, you cannot make B equal to square root of B. Why? Because that value will become less than A. Okay, so that thing you need to take care of. So, what you need to do? either b is a perfect square or it is not. If it's a perfect square, if square root of b is greater than equal to a, then you do b equal to square root of b and you say answer plus plus. If square root of b is less than a, then you understand if square root of b is less than a, then now you are never going to take square root of b because that will always be less than a. For example, if square root of 36 is less than 10, you do b minus minus and take b to 25. Now, if you do again square root of b, this will obviously be less than a, because if square root of 36 is less than a, square root of 25 will obviously be less than a. So, only thing you can do is do b minus minus until it becomes equal to a. So, if it's a perfect square and square root of b is less than a, then you say answer equal to answer plus b minus a, and you do b equals to a, because you just do b minus minus how many times it is required to make equal to a. For example, b is 36 and a is 10, then do b minus minus 16 times. Okay, so b will become equal to a. Now you can use b minus a, you can use 16 loops to do b minus minus, or you can directly do this. If you directly do this, it will save your time. Okay. Now, when it's not a perfect square, you obviously have to do b minus minus. Okay. But what you will do is, you will try to take it to nearest square, perfect square. So that after you reach to nearest perfect square, you can do b square root of b. Okay. So, for example, if b is, let's say, 36 and a is 3. So, you'll do b minus minus, let's say this is 34. So, you do b minus minus until you reach the nearest perfect square. Once you reach the nearest perfect square, this will take 9 steps. Once you reach the nearest perfect square, just find square root of b, because that will give you in one step only from 25 to 5. So, how can you reach to nearest perfect square? So, what you do is, you find square root of b. So, b is 34. So, square root of b will be 5. Okay, it will not be 6. So, it will be 5, right? Because 5 into 5 is 25. Now, what you do is, let's say you stored this square root of b in a variable square root. So, now you say b minus square root square. So, this will be 34 minus 25. So, this will take 9 steps and your b will be equal to this sq square. So, that will be equal to 25. That is nearest square. Okay. But you also do this when this square root into square root is greater than equal to a. For example, if your b is 34 and your a is 30, then there is no point going to nearest square root 20, nearest perfect square 25. Are you getting my point? Because you do b minus minus and you'll reach here only first. So, when it's not a perfect square, what you do is, you first of all find square root of b. Then, if a square root into square root is greater than or equal to a, then you say b is answer is equals to answer plus b minus square root into square root, and b is equal to square root into square root. So, you basically go to the nearest square root in this many steps by doing b minus minus. And if this is less than a, then you will reach a only first. For example, your a is 30 and this is 25. So, from 34, you will reach 30 only first. So, you will say answer is equal to answer plus b minus a. You will do b minus minus this many times and you will say b equals to a. Okay. So, this will be the steps. So, how are you reaching the a equal to b fastest? By making b as small as possible in one step, but making sure it does not go below a. Okay. So, let's look at its code. So, let me move it to the editor. So, first of all, I have taken answer as 0 and sq as square root. So, if a is greater than b, return minus 1. Now, if a is less than equal to b, so while a is not equal to b, we'll repeat this process. First of all, find square sq is equal to square root of b. Okay. So, how will you know if b is a perfect square of b is a perfect square or not? If ignore this line for now. So, if square root into square root is equals to b, it means b is a perfect square. For example, b is 25, so you will get sq as 5. If b is 28, you will get sq as 5. So, 5 into 5 is 25, which is not equal to 28. Okay. So if b is a perfect square, then you operate like this, otherwise you operate like this. So if b is a perfect square, you convert it to square root, that is sq, but you convert it to square root only when square root is greater than equal to a, because you do not want to go below a. So if square root is greater than equal to a, answer plus plus, because this will take only one step, b equal to square root of b and b equal to square root. If square root is less than a, it means you have to reach a by doing b minus minus. So that will take how many steps? B minus a. So answer equal to answer plus b minus a and b equal to a. Now if square root is not a perfect square, then you need to go to the nearest perfect square, that is square root into square root. But you only go there if it is greater than equal to a. So if it is greater than equal to a, then answer equal to answer plus b minus square root into square root, and b equals to square root into square root, that is nearest perfect square. And if it is less than a, then you will reach a first by doing b minus minus. So you say answer equal to answer plus b minus a and b equals to a. And finally you return answer, that is minimum number of steps. Now what happens is, sometimes when the value of the integer which you pass in the square root function is very large, it gives like instead of giving the floor value, it gives you the ceiling value. So for example, for certain large integers, if let's say I am taking an example for small integer, but this happens for large integers. So if it is 45, then square root of b will return 6. Okay, but when they are large integer, then in some case it might also return 7. Okay, it will not happen with the case of 45, but for large integers I am explaining you, if it is not a perfect square, it might return you the ceiling of the square root of 45. So it might return 7. And now 7 into 7 is greater than b, right? But we always wanted to find this value, the nearer value. Okay, so now the nearest square root will be 6 into 6, that is 36. Okay. So whenever such kind of thing happens, so here I have put a check. If a square into square is greater than b, it means the square root which we have returned from that function is the ceiling one. So I'll do square root minus minus. Okay. So that's the one if condition. Many people might have missed, but that's the one thing. And then finally you return the answer. So if I submit this code, so we have solved this question successfully. Okay, now let's move on to the third question. Okay, so now let's go through the third question, that is exotic subsequences. First of all, let me explain you this question on OneNote, and then we'll come here and go through it line by line. Okay, so in exotic subsequences, we need to count the total number of exotic subsequences and return it. Okay, so what is the definition of exotic subsequence here? So exotic subsequence is a subsequence. First of all, I hope you know the definition of subsequence. Subsequence is when you delete some or none of the elements from the array or string, the remaining sequence is called a subsequence. So for example, if I have A, B, C, D, E, if I delete some or none of the elements, for example, if I decide to delete A, B and D, so remaining will be C, E. So this is a subsequence. Okay. So exotic subsequence are all the subsequences in which the characters are in ascending order alphabetically. So for example, if I have A, K, B, so A, B is a exotic subsequence, A is a exotic subsequence, B is a exotic subsequence, K is a exotic subsequence, but AK is also exotic subsequence because here the elements are as in the ascending order lexicographically, but KP is not exotic subsequence because here B comes before K and here it is descending. Okay, so this is not exotic subsequence. So we need to count the total number of exotic subsequences. Okay, so all the subsequences in which characters come in increasing order lexicographically or ascending order lexicographically. Yes, there might be repetition. For example, A, B, A is there. Then A is a exotic subsequence. But it should not be like this, Ka or Da or like this. The next element or the elements on the right hand side cannot decrease. Okay. So let's go through the question line by line. So exotic subsequence, you are given a string S consisting of n lowercase alphabets. So we have a string S of size n and all are lowercase alphabets. You have to find the total number of exotic subsequence of this string. A non-empty subsequence, also it should be non-empty, is called exotic if its characters are sorted in lexicographical order. Sorted means ascending. A subsequence D is considered sorted in lexicographical order if for every ij where I and j are between 1 and length of the string and I is less than j. If the index I is less than j, then the element at index I is less than equal to element at index j. Okay. Your task is to count the total number of exotic subsequences of the given string and return the result answer modulo 10 to the power 9 plus 7. You need to return answer mod 10 to the power 9 plus 7. Then the definition of subsequence is given. Okay. And your example is given. For example, string S is F, G, H, A, B, C, D, E. Then A, B, C, A, C, E are exotic subsequence because they are sorted. The characters are sorted in lexicographical order. But G, C, D, F, H, B, these are not because C comes before G. But here C is after G. So this is not exotic subsequence. Similarly, here B is after H. So this is also not. Okay. So here is an example for ACB, total A, B, C, AB and AC. These are exotic subsequences. Okay. So we need to tell the total number of exotic subsequences. Okay. So let's take this example ACBAB. Okay. ACBAB and try to solve with the help of this. See, what can be the brute force method? Brute force method is to generate all the subsequences. So total number of subsequences are 2 to the power n, where n is the length of the string. And for every string, check whether it is exotic or not. And if it is exotic, do your answer plus plus, right? But this will take exponential time, right? We need to solve it in a faster way. So how can we solve it? So what you can do is you can count all exotic subsequences, sorry, you can count all exotic subsequences which end at index I. Okay. Count all exotic subsequences ending at index I. So you calculate this for all the indexes for I equal to 0, I equal to 1, I equal to 2 up to I equal to n. Once you calculate all the exotic subsequences ending at a particular index, you just need to do this summation of all the exotic subsequences ending at index I. So ending at index 0, ending at index 1, ending at index 2 and so on up to ending at index n minus 1, you will get your answer. Okay. Now, how can you efficiently calculate the number of subsequences ending at index I which are exotic in nature? So, assuming that when you are calculating all the subsequences which are exotic ending at index I, you have already calculated the number of exotic subsequences ending at index 0 to I minus 1. 0, 1, 2 up till I minus 1. Since you have already calculated this, with the help of this, you can calculate this very easily. Why? Because let's say the character here is D. So, here from 0 to I minus 1, you need to see all the subsequences which we have calculated till now, whose ending character is either A or B or C or D, and add that amount. So for example, there are 10 subsequences ending at index 0 to I minus 1 whose last character is A, for example. Then to all these 10 subsequences, you can add this D at the end. So this will generate 10 more exotic subsequences which will end at index I. Similarly, let's say there are 5 exotic subsequences which are ending at index 0 to I minus 1 whose last character is B. Okay. So what you can do is for all these 5 subsequences whose ending character is B, so if the last character is B, all the P4 characters will be less than equal to B because these are exotic in nature. You can simply add D at the end for all these 5 subsequences. So there will be plus 5 subsequences ending at index I which will be exotic in nature. Similarly, for all the subsequences which are exotic in nature ending at index 0 to I minus 1 and whose last character is C, let's say they are 7. So to all this string, you add D at the end. So this will give you 7 more exotic subsequences ending at index I. And now there are, let's say, 3 exotic subsequences whose last character is D, and they are ending 3 exotic subsequences whose last character is D and their ending index is between 0 to I minus 1. So to all these subsequences at the end, if its ending character is D, you can add one more D, that's okay. So it will give you 3 more exotic subsequences ending at index I. So this 10 plus 7 plus 3, 20 plus 5, 25 subsequences will be there, which will be ending at index I and which will be exotic in nature. And you will do plus one more. Why? Because this D individually will also be one exotic subsequence. So all the subsequences whose ending index is between 0 to I minus 1 and whose ending character is either A, B, C or D, their sum which you will take, because to all that subsequences you can add D at the end and get the exotic subsequence, and this one individual D. So plus 1 for that. You have to do this for all the indexes from 0 to n minus 1 and this will give you your solution. Okay, time complexity will be big of n into 26. Okay, let's go through the code so you will understand it better. Okay, so I have taken answer equal to 0, mod as 10 to the power 9 plus 7 and some variables I, j, k and sum, and I have taken count of 26. So when I am at index I have this count of 26 array calculated, in which count of 0 will denote the exotic subsequences ending with character A from index 0 to I minus 1. Count of 1 will denote the number of exotic subsequences ending with character B from index 0 to I minus 1. Similarly, count of 2 will denote for C. Okay. So first of all, I have made all the count to be 0 and n as the length of the string. I have taken this sum variable to calculate the number of exotic subsequences ending at index I on every iteration, and then I will add it to my answer. Okay. So for I equals to 0 to n minus 1, I will traverse the string. First of all, I will find which character it is. So k equal to s of I minus 97, because 97 is the ASCII value of character small a. And similarly, I will find j. Okay. Now I will take sum equals to 0, and while j is greater than equal to 0, I will say sum is equal to sum plus count of j modulo mod. So count of j will have the exotic subsequences whose ending character is j. So for example, if j is 2, then ending character is c, and they are from indexes 0 to I minus 1. Okay. How do we know it is from 0 to I minus 1? Because if we are at index I, we have calculated till 0 to I minus 1 only. So I will add that and then I'll do j minus minus. So for example, by default j was 3, so it will denote D. Then I will do j minus minus, so it will denote C. Then I do j minus minus, it will denote B. Then I will do j minus minus, it will denote A. Then I will do j minus minus and come out of the loop. So if this j was D, then all the subsequences ending at D, C, B, A and having all the exotic subsequences and having index from 0 to I minus 1 are added to my sum variable. Then I will say count of k. K is the current, like k if it was 3. So the current character is D. Okay. So I will say count of k means the number of exotic subsequences ending with D, ending at index I and the last character D is equal to counting of k plus sum, that is the subsequences calculated till here, plus 1 for the individual character modulo mod. And finally, I will take the sum from 0 to 25 of count of I, which denotes the number of exotic subsequences ending at character A, B, C and so on. So ultimately, I'll get all the exotic subsequences and I'll return the answer. How much time this will take? So this is n size loop and this will be maximum 26 size loop. So n into 26, which is basically n. You can ignore 26, okay? Or n into different distinct characters, okay? Something like that. So that will be your solution, okay? Let me submit it. Okay, so it has passed successfully. Now let's move on to the last question. So now let's go through this question 4, that is find longest cycle. First of all, let me explain you this question on OneNote along with the help of an example. Then we'll go through the question line by line so that you understand it better. Okay. So find longest cycle. So first of all, let me take here in this question, you are given a tree with n nodes. Okay. So first of all, let me take one tree. Let's say we have 1, 2, 3, 4, 5 and 6. So you have a tree with n nodes. Now in this tree, you will be given q queries and you need to answer each query. For each query, you will be given two nodes. That is, let's say you are given 4 and 6. So what you need to do is you need to connect the least common ancestor of these two nodes with any other node in the tree such that the cycle formed is of maximum nodes, is of maximum length. For example, in this query, you are given nodes 4 and 6. So the least common ancestor, LCA. What is the meaning of least common ancestor of two nodes? See, ancestor means any node which occurs on the path from current node to the root node. So for 5, 2 and 1 are its ancestor. For 6, 5, 2 and 1 are its ancestor. What is the meaning of common ancestor? A node which is ancestor to both of these nodes. So for 4 and 6, 2 is a common ancestor and 1 is a common ancestor. What is the meaning of least common ancestor? It means which comes first. So for 4 and 6, 2 comes first. So this is the least common ancestor, right? 1 is after that. So 2 is the least common ancestor. So first you find the least common ancestor of these two nodes, that is 2 in our case, and then you connect this least common ancestor with any node in this tree such that the cycle formed is of maximum length. So let's say if I connect 2 with 3, so this will be the cycle formed 1, 2 and 3 with 3 number of nodes. Or you could have connected 2 with 6, then 2, 5 and 6. This cycle will also be of length 3. Right? So there may be multiple possible ways. So you need to tell what is the maximum length cycle formed when you connect the LCA of the given two nodes in the current query with any node in the given tree. Okay, that's the question. And remember, each query is independent of another. So if I connect 2 and 3 to answer this query, that 3 is the length of the longest common cycle, then for the next query, we will again have the same tree. Okay, these edges will go away. So queries are independent of each other. Now let's go through the question line by line. Imagine a city with a complex road network where intersection nodes are numbered from 1 to n. So the nodes are 1 to n and the roads connect some of these intersections. Basically, there are edges forming a tree-like structure. So it is a tree. The main intersection or the root, main intersection means the root node of this network is intersection 1. So node number 1 is the root node. You are the city planner and you have been given a list of queries, each of which contain two intersections. Intersections means intersection of edges, means nodes. Okay. So you are given two nodes for each query. For each query, you are asked with the following. Okay. Find the nearest common meeting point, lowest or least common ancestor for the two intersections. So you find LCA. Once you have identified this common point, you have the opportunity to build a new road connecting this LCA to any other intersection in the city. So connect the LCA with any node in the tree. Your goal is to determine the longest possible cycle. So after connecting the LCA with any node in the city, any node in the tree, what is the length of the longest cycle formed? Okay. That can be formed in the city's road network by adding this new road after identifying the LCA for the two intersections. Each query is independent, meaning the result of one query do not affect the others. For each query, you need to find and report the maximum length of the cycle that can be created in the road network after constructing the new road. This problem essentially simulates urban planning with road construction decisions to maximize the connectivity and possible routes in the city. So this was the example which I took. So now let's think about the solution. So for example, for this query 2 was the LCA. So if I connect 2 with 1, then it will form cycle of 2 nodes only. So better connect it with 3, it will form cycle of 3 nodes. Okay. So I'll divide this question into two parts. So for this question, I'll divide it into two parts. First is finding the LCA, that is least common ancestor, and another is finding the longest length cycle. Okay. So first, let's look at LCA. How do you find the least common ancestor? So I will not go into all the approaches. I will directly tell you the most efficient way in which you can find the LCA in log n time. Okay. But before that, you need to pre-process the tree. So basically what we will store is, for every node, we will store its parent at level 1, at level 2, at level 4, at level 8, at level 16, at level 32, and so on. Okay. But according to the constraints, if you see, the level will not exceed 2022. Okay. So for example, what I mean by that. So basically I see. Okay, cut here and continue from the login part. Okay, so what we will do here is for every node, we will store its parent at 2 ki power 0 distance, 2 ki power 1 distance, 2 ki power 2 distance, 2 ki power 3 distance, 2 ki power 4 distance, and so on. And since the number of nodes are going till 10 ki power 5, so you will not need to go beyond 2 ki power 20 or 22. Okay, so you will find the parent at 2 ki power 0 level. So what do I mean by that? For example, let's say I have this is a part of the tree which I am drawing 1, 2, 3, 4, 5, 6. So for 6, parent at 2 ki power 0, that is 1 level up is this, 2 ki power 1, that is 2 level up is this, 2 ki power 2, that is 4 level up is this, 2 ki power 3 will be 8 distance away, and so on. We are not calculating every level parent. Okay, so first of all we will calculate this. Okay, so how do we calculate this? So I can say parent of a particular node at height 2 ki power x is parent of a node at height 2 ki power x minus 1. And what will here come? It will come parent of node at height 2 ki power x minus 1. So how does this work? I'll let you understand. See, for this node, I need to find its parent at a distance 2 ki power x. So its parent at distance 2 ki power x minus 1 will be here. That will be parent of node at distance 2 ki power x minus 1. That will you will get it by here. Okay, and that node's parent at distance 2 ki power x minus 1. So this node at distance 2 ki power x minus 1 and its parent at distance 2 ki power x minus 1 will ultimately give you this. So parent of a node at distance 2 ki power x is parent of node at distance 2 ki power x minus 1 and 2 ki power x minus 1. Okay. Now since we are only storing the parents at distance 2 ki power 0, 2 ki power 1, 2 ki power 2, 2 ki power 3 and so on. So instead of storing this 8, 4, 16 and so on, we will only store the powers. So if I write parent of node at a distance x, so this basically means at a distance 2 ki power x. So instead of 2 ki power x, we'll use x. So this will become x minus 1 and this will also become x minus 1. Okay, so we will use dp to calculate the parent of all the nodes at distance 2 ki power x. Okay, 2 ki power 0, 2 ki power 1, 2 ki power 2 and so on. So first of all, let me show you that code. Like from the complete code, we'll understand that part. Then we'll move further. Like how is this been calculated? So let me move this code here. Okay, and let me go in full screen. Okay, so here you can say up n plus 1 22. So this is basically storing the parent. Okay, so node at upside of the ith node at a distance 2 ki power I. So if here I am writing for 18, it means 2 ki power 18. Okay, since there are 10 ki power 5 nodes according to the constraints at max, you do not need to go beyond 22. Okay, so this is for that. This is to store the adjacency list. In the input we are given n, q and the ages and the queries. Okay, so then I have taken some other variables. Don't worry about that right now. And what I'll do is I'll traverse the edges and form the adjacency list. Okay, then I'll call DFS. So if I look at DFS, so if node is 1, it means in DFS I am also passing parent. Okay, so you can see here for this is the node and this is its just parent, because see, for parent we are storing in this. For parent of node at a distance 2 ki power 1 is parent of a node of its parent at distance 2 ki power 0 and its parent at 2 ki power 0. But parent at 2 ki power 0 you cannot write with recursive equation. That's the base case you have to write. So parent of node at distance 2 ki power 0 is equals to parent. This you will write by yourself and then apply this recursion relation. Okay, so if I go here and look, So if it is, so here I am passing node and its parent. Okay. So for node number 1 from root, I am starting the DFS and its parent I have marked -1 because 1 is the root node. So if node is 1, then its parent at distance 2 to the power 0 will be this node only itself, because this is -1 we are passing now. So -1 is not a valid node. So parent of node 1 is node 1 only. Now why am I writing this? Because let's say I write a parent of node, a particular node. Let's say you have 1, you have 2, and you have 3. So parent of 3 at 2 to the power 1 distance is this. Parent of 3 at 2 to the power 2 to the power 0 distance is this. 2 to the power 1 distance is this. There is no 2 to the power 2 distance. But I will be writing the parent of this at 2 to the power 2, 3, 4, 5 all. So I will mark them as 1 only. Okay. So if node now it is root node, then parent at level 0 is this only. Otherwise, it is the just parent which we will pass. Okay, how we will pass it? So when we will call DFS for a particular value in the adjacency list, we will set that the current node is its parent. Okay. So when I'll call DFS on 3 from 2, I'll pass 2 as its parent, immediate parent. So otherwise, the immediate parent is parent. And now I'll use this recursive relation for I equals to 1 to 20. Parent at at distance 2 to the power I is parent of parent node at distance 2 to the power I minus 1, and its parent at distance 2 to the power I minus 1. Okay. And it would be already calculated because we are going from I 1 to 20. Then I will mark it. So I am not going here right now. Okay. So that is how we will store the parent of at distance 2 to the power 0, 2 to the power 1, 2 to the power 2, and so on. Okay. Now, once we have stored that, and we have a query. Let's say I have a query. This is node 1, node 2, node 3, node 4, node 5, node 6, node 7, node 8, and node 9. Okay. Now I want to find the least common ancestor of 6 and 9, which is 2. Okay. So what I will do is, first of all, so for what I'll do is I'll start from, for 6, I'll start with the highest node. Like the parent of node 6. Parent of node 6 at a distance 2 to the power 20. I'll start from there and see whether it's a common ancestor between 6 and 9. So I'll move from top and I'll come bottom and I'll find the first node which is not the lowest common ancestor of 6 and 9. So what is the first node which is ancestor of 6 but not a common ancestor of 6 and 9? 4, right? Because 2 is a common ancestor, 1 is a common ancestor, 4 is the first node which is ancestor of 6. Like if here let's say it was 8 and here it was 10 and I need to find between, let's say this is 18. I need to find between 18 and 10, or let's say this is 11. And if I want to find between 11 and 10, it would be node 4. It's the highest ancestor of 11, which is not ancestor of 10, because after that 2 is ancestor of 10. So I'll reach to 4 efficiently and then I'll return its immediate parent as its ancestor. Okay. So what I will do is, I will start from the very top, at a very large distance, whether the parent of 6, or parent of 11 at distance 2 to the power 20 is common ancestor or not. Then 2 to the power 19 is no, yes or not. If 18 is yes or no, and so on. Okay. So what I'll do is, let's say I'll do it for 10. So for 10, this is at distance 1, this is at distance 2, and this is at distance 4. Okay. So this will be the common ancestor. This at distance 2 will not be a common ancestor, right? So I'll move here. So now I am at node 8. Now for node 8, last jump was of size 2. So next jump will be of size 1. If a jump is of size 16, next jump will be of size 8, then 4, and so on. So I'll again do a jump of size 1 if this is not a common ancestor of 11 and 10. So I'll again jump. So I'll find 5. Now I'll not do a jump because now this is a common ancestor. So we'll stop here and I'll return its immediate parent. That would be the common ancestor. Okay. So let me explain it to you here in the code. Okay. So what I'll do is, see here. whenever for any query I want to find the least common ancestor, I'll pass the node values, okay? And this least common ancestor, first of all, it will see if u is an ancestor of v, return u. If v is an ancestor of u, return v, because that would be the least common ancestor of u and v. If not, run a loop from I equal to 20 to 0, and if this 2 ki power ith distance parent of u is not an ancestor of v, here I have marked not, then u is equal to that ancestor of u at distance 2 ki power I, and I'll keep doing this. At the end of this, I will be at the node which is just below the least common ancestor. So I'll return its immediate parent, which will be least common ancestor. Okay. Now, whether two nodes, whether this first node is an ancestor of second or not, for that I have called this is ancestor function. So how does that work? Let's see. So what we will do is, when we will do the DFS run, we will store the in time and out time of all the nodes. So for example, 2, 3, 4, 1, and let's say 5, and let's say 6. Okay. So if I start DFS from here, this will be time 1, time 2, time 3, time 4. Now all of its children are done. So time 5, then from here I'll go here. Okay. So this will be time 6. Then all of its children are done. So time 7. Then when will I exit from node 3? Time 8. Then I'll go here and go here. So this will be time 9 visited, time 10 exit. This will be time 11 exit, and this will be time 12 exit. So if u is an ancestor of v, then the in time of u will be less than v. It would be visited first, and out time of u will be greater than v, because v will be exited first. So u will be visited first and v will be exited first. So for example, 2 is an ancestor of 6. So its in time is less than 6, and its out time 11 is greater than the out time of 6. So 2 is an ancestor of 6. Okay. So that is how I am getting here in is ancestor function. If a and b are equal, then obviously they are ancestor, a is an ancestor of b. Otherwise, if in time of a is less than in time of b and out time of a is greater than out time of b, then return true. Otherwise, return false. When are we calculating this in time and out time? So you can see here, when we ran the first DFS, I said in time of node is equal to time plus plus, and after traversing all its children, I said out time of node is time plus plus. So till now we calculated the least common ancestor. Now we need to think, once we calculated the least common ancestor, with which node we will connect to that node 2 to get the maximum length cycle. So once we have found the LCA, that is least common ancestor, how can we find the maximum length cycle? So see here, there can be two possibilities for maximum length cycle. Let's say this is node 1, 2, 3. Let's say this is 4, 5, 6, and 7. Okay. Now let's say the LCA, the query was 4, 6. So the LCA of 4 and 6 is 2. So the longest cycle which you can form is by connecting 2 to 7. Okay. Now if there were more than 3 nodes below 4, then you would have connected there. Here you are connecting it with this. That will give you the longest length cycle. So how you are getting it basically? Number of nodes in the right child, like the length of the subtree in the right child and the length of the left subtree in the left child, plus 1, the maximum of both of them. So left is 1, right is 3, and plus 1 will give you what? The maximum of this, that is 4. So there will be 4 nodes in the cycle. There could be one way this, you connect with either of the children. There can be multiple child as well. Okay, there can be 3, 4 layers also. So you connect the longest length subtree among the children. That will give you maximum length cycle. Another could be, it might be possible that here you have, let's say, 8, 9, 10, and 11. So it might be possible when you connect 2 with 11, it will give you the longest length cycle, that is 2, 1, 8, 9, 10, 11, and 2. Are you getting my point? So it is parents. Among the parent, you see their children's longest length other than this child. So one is this and other is this. So you find that this is the longest length, and connecting it with here will give you the maximum length cycle. It may be parent child also. So it might be possible here you have, let's say, 12, and then you have a very huge cycle. So you might connect this 2 with here also. Okay. So first we'll see how you can manage this maximum length subtree among the children, and then about the parents. Okay. So I have taken two arrays which you can see. One is DP and one is DPP. So DP is for children and DPP is for parent. Like parent and the via parent, what is the longest length which you can get. Okay. So when I call DFS1, if the count is 0. Now what is count? Count is a variable which you do plus plus, which was initialized to 0, and you do plus plus whenever you visit during the DFS any of the children. So if count remains 0, it means it's a leaf node. So if it's a leaf node, then DP of node is 0. Why we are taking 0? Because we are not counting the current node. Okay. So the length of the subtree of any of its children is 0 because it's a leaf node. And if it is not the leaf node, then it is 1 plus mx. Now if I see mx is what? It is initialized with 0. And it is maximum of DP value of among its children after you do DFS on their children. So you calculate the DP value for its children and then the maximum you store it here. And why do you do 1 plus? Because see, we are not storing the current node. So for example, this is 1, 2 and 3. So DP value for 3 will be 0. This will be DP node for 3 will be 0. For this it would be 1. Now, when you see that its child DP value is 1, but this 1 means it has 1 children. This current node we don't count. So, here I need to say DP of 1 is equal to DP of 2 plus 1 because I need to count 2. Right? I will not count 1 in DP of 1. So, the longest length subtree of children is 2. So, that's why we do plus 1. So, in that way we store using one DFS, we store the DP value for all the nodes. Okay, now let's come upon DPP value. So that I store using the second DFS. Okay, so here if you see DPP2, so if the node is 1, if it means if it's the root node, there is no parent of the root node, so for that DPP will be 0. Otherwise what we do is we say max is equal to DPP of parent. So for parent, so for this is the current node. So this is the current node, let's say 2. So for its parent 1, what is the maximum length through its parent? Like if there are parents, okay, DPP is via parents. So this will store all the ancestors, like this is 2, this is 1, and if there are other ancestors, so DPP of 1 will give you all the paths via 1, okay, via its ancestor, the longest length of that. But you need to see the 1's children as well, because this DPP of 1 will give you the path via its parent. So now you just need to cover the case where you consider the children of its immediate parent, because its children are covered in DP, okay. So you say, so first of all you store DPP of parent, which will cover the via parent all the above paths. And now you traverse its adjacency list of the parent, and if the value of that node it's not equal to current node and it's not equal to the parent of parent, so it's the children of its immediate parent other than current node, then I will say mx equal to max of mx and 1 plus dp value. So what is the for its immediate children, immediate parent, the children length, okay, that is mx dp of value and 1 plus to that, because we don't count the current node. And finally dpp of node will be equal to 1 plus mx, right, because we do not consider the immediate parent while calculating these values, so we do 1 plus, okay. And then we do recursively DFS. So we calculated dp and dpp, and now for all the queries, first I'll find the least common ancestor, and then I will say 1 plus maximum of dp of lc, that is the maximum length subtree among the children, and dpp of lc, that is maximum length via the parent. And out of that, whatever will be there, I will do plus 1 to consider the current node, and this will give me the maximum length cycle, and I will store it into the vector for each query and then finally return the vector, okay. So let me just run it and show to you. Okay, so we have solved this successfully. I hope you have understood it completely. Thank you.